My name is Šikić. I'm a mathematical logician. I was professor of mathematics at the University of Zagreb, and after retirement, I'm associated with the Center for Logic and Decision Theory at the University of Rijeka. I published 6 monographs, 3 university textbooks, a dozen of high school textbooks, and a few dozens of textbooks in mathematics for elementary schools. What to say? I was president of the Croatian Mathematical Society and the first president of the Croatian Logical Association, and also the first president of the Union of Scientists of Croatia. I published also 55 articles in scientific journals and 70 in professional journals. I'm addressing you as a recipient of Georgius Benignus Award for 2020, awarded by Croatian Logical Society. And the title of the article was Kneale Developments as Notational Variant of Beth's tableaux. Well, I think that's enough about me, and I move now to the presentation of my paper. So here we have the title, Kneale's Natural Deductions as a Notational Variant of Beth's tableaux. In foundation of logic, we have 2 great traditions, syntactic tradition and semantic tradition. Syntactic tradition is connected, of course, with the notion of proof, and semantic tradition with the notion of truth. First, syntactic foundations of logic were axiomatizations of logic, as for example by Frege in 1871 is Hindenburg Griffschrift. He axiomatized first order logic. We can pull out of his much broader system the first order part, and then we have these 3 axioms for conditional and the 3 axioms for negation. This is contraposition, double negation introduction, and double negation elimination. And of course, we have quantification axioms and the rules of inference, which is modus ponens and generalization. It was maybe the first axiomatization of first order logic. Frege's idea was a higher order logic, but we can distill this part, first part, out of it. If you ever worked with such a system, then you know how difficult it is to derive tautologies, formulas from this system. For example, it's not quite trivial to deduce that if A, then A is a tautology. And maybe another example, Lukasiewicz in 1923 proved that was 50 years, more than 50 years after introduction of this system, that the axiom F3 for conditional is derivable from the other axioms. Of course, to do that, you have to use derived rules, because if you work in the axiomatic system itself, it's really cumbersome and difficult. So, of course, the most famous derived rules is deduction theorem, which say if you can deduce B from the assumption A, then you can deduce if A, then B without this assumption, so you can discard this assumption. And you can view this as an introduction rule for conditional, and then you can see modus ponens and the elimination rule of conditional. And of course, you can then introduce other derived rules in this same two-type differences. You have introduction rules and elimination rules for negation then also for conjunction, alternation, but I'll stick to conditional and negation as in the original Frege system, just to save the space and time. And of course, for the quantification, universal and also for existential quantification. But then what you realize is that if you add to this system of derived rules, this introduction of logical constants and elimination of logical constants, if you add double negation elimination, then you actually get what is also an axiomatization of first order logic. So then we call this, of course, natural deduction system. So if you systematically introduce these derived rules in this two-type fashion, you just finish with the natural deduction system for the classical logic. I don't know if that was the original Gentzen train of thought, but it could be. Maybe it was. More precisely, if we realize, which is quite easy to prove, that elimination of double negation is equivalent to ex falso quadruped plus tertium non datur, then we have the very well-known result that if you have just introduction and elimination rules for logical constants, then what you get is minimal logic. If you add ex falso quadruped, you get intuitionistic logic. And if you add tertium non datur, you get classical logic. And this is sometimes called proof semantics. And it was done originally by Gentzen in 30s and further developed by Pravitz in 60s. Now, we can present this natural deduction system in sequent format. It is just the same system, but another presentation. So, for example, look at this introduction of conditional. If you can deduce B from assumptions gamma and A, then you can introduce if A then B. Just from gamma, you don't need A. This is just the introduction of conditional written in different format. And similarly for eliminations and all the other logical constants. And of course, in this sequent format, you have also the so-called structural rules, which tells you how to start deductions. This is overlap, how to weaken them, and how to glue them. This is cut rule. And we have this is just natural deduction system, but written in a different format, just a notational variant. Now, it is relatively easy to prove, and I think this was the Gentzen's thread of ideas. It is that you can, if you have cut, that you can prove that every elimination rule in sequent form is equivalent to the introduction into antecedent. It is quite easy. And you can do it for every elimination for every logical constant, and then you get the system of introductions into antecedent and introductions to consequence. And this is what we know as Gentzen sequent calculus. And I think that he moved to this sequent calculus just starting from natural deductions, and then put them in the sequent format, and then realizing that you can make these equivalences. And of course, it is usual that contradiction is simulated by empty consequent, and then you get, and of course you put weakening and cut in the appropriate format, and what you get is Gentzen's singular system. So we see that it is just a natural procedure from this natural system to sequent system. And now, of course, we now see that Gentzen's singular system is equivalent to intuitionistic natural deduction system, because this is just introduction and eliminations rules, but eliminations are now introduction into antecedent. And just note how ex falso quadruped is really kind of weakening in this system. And what Gentzen realized, of course, you can add X falso quadruplicate you have, and if you add tertium notator, then you have classical system. But what Gentzen realized is that if he moved to the multipler sequence system, then he can get double negation or tertium notator, and he get classical, something which is equivalent to classical natural deduction system and which have a more of classical symmetry. There is no differences between, let's say, alternation and conjunction and so on, which we see in the natural system and in the sequent form of the natural system. So that was what I wanted to say about this syntactic tradition. Now for the semantic tradition and foundation of logic. In semantic tradition, we found the classical logic on the classical meaning of logical constant. And classical meaning of logical constants is just the classical truth conditions for the logical constant. So let me illustrate this on the conditional. What does it mean that if A and then B is true? It just means that A is false or B is true. And what does it mean that if A then B is false? It just means that A is true and B is false. So you have this self-explanatory format of this analysis of the meanings of logical constant on the left side in green, and you can do it for all the logical constants in the well-known way. Now, what I'm also offering here is so-called Gentzen format, which is, we'll see why I call it Gentzen. It was not originally Gentzen's approach. What I'm doing here is just a notational variant. Instead of symbolizing that something is true like this, I symbolize it by putting it on the left side of the non sequitur sign. And I symbolize that something is false just in a way that I put it on the right side of the non sequitur sign. You can, in a sense, understand that from the meaning of the non sequitur sign, these rules are valid, but we don't need it here. I am just saying that this is a notational variant of the original Beth analysis, and just be aware that we can put it in this format also. And then, of course, we have this Beth testing, how to prove that one formula implies another formula. Let's say this one that implies this one. We just assume that first is true and the second is false, and then we analyze according to the Beth rules what must be fulfilled in this case, and we end in contradictory assumptions, in contradictory consequences. And because the starting assumptions were contradictory, it means that it is always the case that if first formula is true, then the second is true, and this means that we have this logical implication. Now, if you put this Beth analysis in another format with non sequitur sign on left hand side, then if you just rewrite this analysis here, then you realize immediately that if you read this testing from bottom up, that this is just a proof in a Gentzen sequent system. It was folk knowledge in logic, I would say, for quite a long time. But as far as I know, the first who published it and that you can see it in print is Fitting in 1983 in his book on modal logic and tableaux systems. So now we see that Gentzen system is actually equivalent to Beth system. And note also that because there is no cut rule in the Beth analysis, there is also not cut rule in this system. So what is also this? We have here a semantical proof that cut is unnecessary for classical logic, so it can be eliminated. We don't have cut here. of course, the Gentzen's proof of the cut elimination was syntactical and much more complicated. Now, let us move to the Kneale system of multiple natural deductions. He introduced the system in 1962, and his idea was, he had two ideas, I would say. First of all, it was the generalization of natural deduction system to multiple consequences, because we had the multiple consequences in sequence system. So he thought, what about having a multiple consequences in natural deduction system? That was one point. And another one was that he wanted to devise a system of natural deduction, which does not have global rules. And I will just say what are global rules. The rule is global. These star rules are global. Let's look at this one. If you want to conclude from fa to for every x fx, you have to check not just this formula, but all its assumptions. So you have to look at the whole deduction, and they realize that there is no a in the assumptions. So this rule is global in the sense that it's not enough to look at the end formula, but you have to look the whole derivation. But you see his introduction rule for conditional, elimination rule for conditional, then for negation, and also for conjunction and alternation and others. Like all propositional rules in his system are local. Remember that conditional introduction of conditional in Gentzen original natural deduction system was global, because you have to discard assumptions, so you have to look at the whole deduction. So he, in a sense, succeeded to formulate propositional logic with only local rules, not the quantification logic, because he needs this. But in a sense, he was not aware of that, but his system was not complete. We have to introduce, I'll tell something about it later, you have to introduce contraction rules. What is the contraction rule? If you have two identical assumptions, then you may discard one. And if you have two identical conclusions, you may discard one. So these rules are necessary because his system is not complete without these rules. And these rules are not local, they are global, because you have to look at the whole deduction and look if there are identical assumptions or identical conclusions somewhere. The first who realized that his system is not complete were Schollschmidt and Smiley in their multiple conclusion logic from a book from 1978. And for example, they proved there that this simple distribution of alternation through conjunction is not provable without this contraction. As a matter of fact, they were not using contractions. They were using a special cycle. So I didn't say that, but I should say that the proof system of Kneale is the system of graphical proofs, but these are graphs without cycles, so they are trees. So to prove to be valid must be tree in Kneale system. It must be without cycles. And Schollschmidt and Smiley, they relaxed this rule to get a complete system in such a way that some cycles are possible. You can use some cycles, some specific cycles. And our approach, which is equivalent to theirs, is just instead of this special cycles, you just use the contraction rule. And this is easy to prove. I proved that it is equivalent. So now we have this natural deduction system with multiple consequences. And what was my idea is to prove that this system is also just a notational variant of Beth's system. How did I prove that? Well, I proved that Kneale system is equivalent to multiple Gentzen system in such a way that I started with the specific rules of Gentzen system. Let's say this introduction of conditional in the antecedent. And I saw how you can mimic this rule in Kneale system. And of course, vice versa, I can do that. And I do it for every possible introduction into consequent and introduction into antecedent. This is another one. So you see, if you have that from gamma 1, you can deduce delta 1 and A. This is this. And if you have that from beta and gamma 2, you can deduce delta 2. This is this. Then you can apply modus ponens here and connect these two proofs. And what you get that from gamma 1 and gamma 2, you can, and if A then B, you can deduce the two. And in such a way, I show that to every elementary step of multiple Gentzen system, there corresponds a step in Kneale's Kneale system and vice versa. And then by induction, let me show, let's say, okay, similarly for negation, you can imagine you would find these elementary steps by herself if you want, and you can do it also for conjunction and alternation, and here it is for universal quantification. And this, of course, means that A is not in any of the assumptions, and here similar. And then by an inductive argument, starting from these elementary correspondences, I prove that to every deduction in Gentzen system, there correspond to deduction in Kneale system and vice versa. So they are completely equivalent and those step by step. So they are just a notational variant of one another. And in this sense, I prove that that each Gentzen multiple deduction generates, this should be C Kneale deduction, I mean, contraction Kneale deduction. This is a wrong word, and vice versa. So C Kneale's deductions are just another format of Gentzen's multiple sequence deductions, but they are just another format of Beth tableaux. That was this folk knowledge we find it fitting. So finally, we can conclude that Kneale's deductions are just another format of Beth tableaux, which is the result of the paper. And I would say the point of the paper is just to prove that all these systems are just notational variants of a Beth system. And the main idea behind all of this for me was that I think that the classical foundation of classical logic should be in the classical meaning of the logical constant, which is their truth conditions. And if we think of the classical logic in this way, then immediately we realize that the primary system, so to say, of classical logic is Beth system. And then it is quite nice to understand that all the other systems we know, the natural deduction system, sequence system, and so on, are just the notational variant of this primary system. And so this proof we knew for all the other systems in a way that it was the case, but we didn't know that for Kneale system it's also the case. So I proved it, and now I can say, well, we have one primary system, that's Beth tableaux system, and all the other systems are just the notational variants of this fundamental system. So that was my result, and thank you for your attention.